This is part 6 of a series on KNN. In this video, we'll look at the inverse occurrence frequency, IOF, similarity, or distance for handling categorical data. This video was produced in Korean and then translated into English. The audio was generated via AI, text-to-speech. In the last video, we looked at the matching coefficient for handling categorical data, and also looked at the Jaccard coefficient, which is an improvement on the matching coefficient. In this video, we'll look at a more improved way to measure the similarity or distance called inverse occurrence frequency, IOF. We will also look at how to handle data that is a mix of categorical and numerical data. Finally, let's implement a KNN classification model using the IOF similarity. Now let's take a closer look at the inverse occurrence frequency IOF similarity. The Jaccard coefficient we looked at in the last video has a drawback in that it does not take into account the occurrence frequency of each label. Let's say we have a label-encoded categorical dataset like this. The one at the bottom is the test data point, and the rest are training data points. We want to measure the similarity between the test data point C and other training data points. If this data contains a lot of label 2, the labels 2 will match each other a lot. So there will be more training data points that are similar to the test data point. To solve this problem, we can use the inverse occurrence frequency, IOF similarity, which takes into account the occurrence frequency of each label. The IOF measure was originally constructed for the text mining tasks. Later, it was adjusted for categorical variables. The measure assigns lower weight to mismatches on more frequent values, and vice versa. First, we use this training data to create a frequency table like this. This data contains 3 labels, 0, 1, and 2. The feature outlook includes 4 labels 0. The feature temp contains 5 labels 2. We want to use this table to measure the similarity between C and A and between C and B. The feature outlook value of the test data point C is 1. The value of the feature temp is 2. And the value of the feature windy is 1. The feature values of the training data point A are 2, 1, 1 respectively. Now let's compute the IOF similarity between the data points C and A. The IOF similarity is defined as follows. This formula is taken from this document. Let the feature values of C and A be represented as X and Y, respectively. If X and Y are identical, the similarity between them is defined as 1. Where K is the feature number 1, 2, and 3. If X and Y are not identical, the similarity between them is defined as follows. The function f denotes the frequency table. x1 is the outlook value of C, i.e. label 1. f1 of x1 is f1 of 1, which is 4. y1 is the outlook value of A, i.e. label 2. f1 of y1 is f1 of 2, which is 5. So the similarity between C and A for the feature outlook is computed as follows. This is 0.309. When X and Y do not match, the higher the occurrence frequency, the larger the denominator, and thus the smaller the similarity. That is, the higher the occurrence frequency, the more a kind of penalty is imposed on the similarity. The features temp of C and A are X2 and Y2 respectively. If we compute the similarity for the feature temp in the same way as above, we also get 0.309. For the feature windy, X3 and Y3 are identical, so by definition the similarity is 1. Now that we have computed the similarity for each feature, we average them to compute the similarity for all features of C and A. The result is 0.539. The IOF distance is defined as follows. Then the IOF distance between C and A is 0.855. If we compute the IOF similarity between C and B in the same way as on the left, we get 0.743. And the IOF distance between C and B is 0.346. Therefore, the test data point C is closer and more similar to the training data point B than to A. Next, we'll look at how to handle data that has a mix of categorical and numerical features. This data has 3 categorical features and 1 numerical feature. The feature X consists of continuous real-valued numbers. The first method is to convert numerical features into categorical. There are many ways to convert numerical data into categorical data. For this, we can use the methods such as equal width binning, equal frequency binning, percentile, and k-means clustering. The example below shows how to convert the feature X into 4 categories using percentiles. The sorted feature values are divided into 4 buckets as follows. Each bucket contains roughly the same number of values. Each bucket contains 25% of the feature values. The code to convert the values of feature X to X prime can be written as follows. Compute the qth percentile of X. P1 is the 25th percentile. P2 is the 50th percentile. P3 is the 75th percentile. Assign a bucket number to each data point that falls into that bucket. The results are as follows. These 4 features allow us to perform KNN by measuring IOF similarity or distance, as we saw on the previous page. The second way is to handle categorical and numerical features separately. Let's look at 2 examples of this case. Let's look at our first example. For categorical features, compute the IOF distances. For numerical features, normalize the feature values and compute the distances such as Manhattan. Then, we compute the weighted average of the 2 distances. The IOF distances on the categorical features computed on the previous page are as follows. And the Manhattan distances computed with the normalized feature X are as follows. These results were obtained using the code below. Next, we compute the weighted average of these distances. The average distance between the data points C and A can be computed this way. Since we have more categorical features than numerical features, we can give more weight to the IOF distance. These weights can be considered hyperparameters. The data point C is closer to B than to A. Next, let's look at the second example. Perform KNN on categorical data and find K1 neighbors for the test data point. And perform KNN on numerical data and find K2 neighbors for the test data point. Then we predict the final class of the test data point by majority voting on the K1 plus K2 neighbors. K1 and K2 are also hyperparameters. Next, let's write code to perform KNN classification using IOF similarity. We will use the following simple dataset that was used in the previous video. This dataset consists of categorical features. It was taken from this site. The names of each column are as follows. The results of one-hot encoding this data are as follows. Now, we write a function that computes the IOF similarity between a test data point and a training data point. For example, if the first row of this data is the test data point and the remaining rows are training data points, we compute the IOF distances between this test data point and all training data points. The Q table is an occurrence frequency table generated using the training data points. The first column of this training data contains 10 zeros, and it contains 4 ones. We use this Q table to compute the IOF similarities between a test data point and a training data point, and return the average similarity. Next, we write a function that predicts the class of the test data. The input X is one-hot encoded or label encoded feature data, and the input Y is the target class. K is the number of neighbors used in KNN. Take data instances one by one from feature data X and generate test data and training data. In the first round, we use the first instance as a test data point, and the rest as training data points. Generate an occurrence frequency table using the training data. We compute the IOF similarity between the test data point and all other training data points, and store the results in the similarities list. Then, we choose the K neighbors with the highest similarity to the test data point. We predict the class of the test data point by majority vote. And we store whether ypred and ytest match or not in the match list. If they match, true is stored, otherwise false is stored. The ypred is the predicted class, and the ytest is the actual class. Print the prediction results to the screen. In the second round, we use the second instance as a test data point and the rest as training data points. This process is repeated until the last instance is used as a test data point. Finally, we measure the accuracy using the true and false values stored in the match list and return the accuracy. If there are 7 trues and 3 falses, the accuracy is 70%. Now, let's use the function predict to classify the categorical data. First, we one-hot encode the data. The encoded data is as follows. The last 2 columns are the encoded target classes, and the remaining columns are the encoded feature data. The variable x is the encoded feature data, and the variable y is the encoded target data. You can use the last column as your target data. The k-value of KNN was set to 3. We measure the accuracy by calling the function predict we just wrote on the left. The results are as follows. If we use the first instance as a test data point, the true class is 0, and the predicted class is also 0, so they match. The results for the remaining instances are as follows. 10 out of 15 are true, so the accuracy is 66.7%. Next, we'll use label encoding. The encoded data is as follows. Using this data, we do the same thing we did on the previous page. The results are as follows. In this case, too, we achieved an accuracy of 66.7%. Let's run this code. The results are as follows. So far, we have looked at the IOF similarity or distance. In the next video, we will look at the KNN regression algorithm.